Hello there, I'm Teacher Monday Dennis Maximus. I'm back with A-Level Physics Paper 1, Section B. This is the third lesson of heat. And having looked at the first two types of thermometers, we looked at the liquid in glass and even the constant volume gas thermometers in lesson 2, B002. Now in B003, which is our lesson 3, we would like to explore first of all the platinum resistance thermometer, and later on we shall also look at the thermocouple. Okay, a platinum resistance thermometer is a simple thermometer which operates on a simple thermometric property called the electrical resistance of a pure platinum wire. Now we all know very well that as the temperature of a substance, of a metal to be specific, if the temperature of a metal is increased, then its electrical resistance should also increase. And if a pure metal, the relationship is linear. In simple terms, the electrical resistance is directly proportional to the temperature. So we can use that as a thermometric property. Electrical resistance of a pure platinum wire is the thermometric property. Now, to get the unknown temperature, if you are on the Celsius scale, basing on the Celsius scale, you need the R theta, which is the resistance at the unknown temperature. You subtract R naught, which is the resistance at the ice point, and then divide by the difference between the resistance at the upper fixed point or the steam point, and the difference between the resistance at the upper fixed point and the resistance at the ice point. So that's how we get, you multiply times 100. So the expression is right here. And then on the Kelvin scale or the thermodynamic scale, we get the resistance at the unknown temperature, divide by resistance at the triple point of water, and you multiply by 273.16, and whatever we shall get shall be in kelvins. Yes, so this is theta, but observe that the second theta is in Kelvin, the first theta is in degrees Celsius, so they can't be the same values definitely. And in many books, instead of using theta here, they use a T. So it's easy for you to understand. I'll just take it like that for purposes of uniformity here. Now, I've already talked about what each of these parameters here represents. Alright, so what is the structure of a platinum resistance thermometer? How does it look like? A platinum resistance thermometer is very simple, very basic. Let me try to magnify this so you can see. Okay, first of all, we have a Wheatstone bridge, and it's built in such a way that here we have a battery. It can be a battery or just a cell, one cell like it's represented here. Then we have two standard resistors, P and Q, and they are always made the same. They are of the same value. P and Q are two standard resistors of the same value. We have a center zero galvanometer. Then we have a resistance box. In some books they will say rheostat. This is a resistance box because for a resistance box we are able to know the value of the resistance. And then down here, coming down, we have two leads. So these are just copper wires that lead to now the silica tube. This is a silica tube. The silica tube which we have here has two leads. One from the side which has the resistance box, one pair. These are two leads. One pair coming from this side where there is a resistance box, and then the other pair coming from this side or where there is no resistance box. But this other pair which comes from the side where there is a resistance box is just circuited down. So we will have these two coming, and then here they just connect. You connect. That means this wire comes and then moves up like that. Then these two leads, for them they go to the platinum wire. So they go to the platinum wire, which is wound around a mica, some mica piece here. So you have some mica piece, and then you wind around it the platinum wire. And then to space and to avoid these two from touching, you space using the mica spacers. They are here, the dummy leads and the leads to the platinum wire. They have to be spaced using some mica spacers. So if someone asks you to draw this, are you able to draw it? Yeah, you can draw it. Someone may say it's hard. It's not hard to draw. It's not hard to draw. Basically, what you need is maybe, I don't know whether I can increase the size. Okay, it may be very hard for me to increase the size of the pen that I want to use here. But basically, what you need to know is drawing up here is easy. You'll have, let me try to reproduce this. You'll have just a simple cell, that is a cell. Then, okay, we will have here two resistors. That's resistor number 1. And then we make that kind of conjunction. This is resistor number 2. And then we baptize them. My drawing is weird. So this is resistor P and this is resistor Q. Okay, then here we can have the center zero galvanometer. Very good. Center zero galvanometer. Then here we will have, we need to leave a space. Okay. Then we have another junction here. Then we are going to leave now also a space. Then this also goes now to a variable resistor. The variable resistors are basically of two types. We can have a rheostat or a resistance box. But we are choosing a resistance box for purposes of being able to measure our resistance, sorry. So now we have leads. These are just copper wires. Leads. These leads, 2 of them coming from each of these gaps. Like that. Now, actually, there are many books that draw and stop just here. They just stop here. And then, once you've drawn this, this side here is going to go to the actually other books just to do this, meaning that the platinum wire is long, but we wind it around. I think I'm going to erase this part here. Let me just erase. Okay, we wind it around. The part which confuses students is this one here. Just this one. The first part is easy. Up is easy. But now this part here down. So let me try to redraw it. If you have the 4 leads, 2 pairs, this other one is the dummy. The dummy is easy for it. You just come and then you connect them down. They go back. That is very easy. Now these ones which come to the mica piece that are wound, for it you come like this. Then you put some piece of mica. So we have some piece of mica here. Okay, and then now we show that it was wound, so that those leads, they come to some platinum wire. That is now, this one here is coming from this part here, then the other one is coming from the other one, this one here. You don't need to indicate these dotted parts. I'm just trying to show you where they come from. Then from there, so the winding continues. Bring the 2, even this one will come like this. So we are taking them around, wind like that. Even here we take this one around like that. Then we wind again. So we may wind, but remember the 2 end up also connecting like that finally. And then this is the whole of this setup here is enclosed in a mica tube. As simple as that. You see? So we can space them, we can indicate and put the mica spacers like this. You see? The mica spacers. So you can draw this in a very simple, even in an exam. As long as you know how to come with these two leads, these two, the dummy leads, for them, you just short circuit them. Just connect them one to another. But these other two leads, for them, you come with the two of them, where I've put those 2 points. You come with the two of them, and then you connect them to the platinum wire, which is wound around the mica piece, like that. So that's how we handle that. And I want you not to take it as something hard. All right. Now, having known now how to draw a platinum resistance thermometer, we need to understand how it works. Okay, we're going to say here that the platinum wire is wound on strips of mica. So, by the way, these two strips of mica, it's not basically one piece. They're usually perpendicular to each other. They're usually two strips perpendicular to each other. You can see, for example, in Nelcon and Parker, they bring it out properly. So the platinum wire is wound on strips of mica and connected to copper leads for connecting them to a Wheatstone bridge. So let's get this. The platinum wire is wound on strips of mica. So we have two strips of mica, but not well represented here. You'll have one strip might be like this. They're usually perpendicular to each other, though we don't need to go into details of showing. Then another one, this one passes through the other one. So you'll find in 3 dimensions, so that's how they look, like that. So they wind around in that kind of way. And connected to leads, copper leads, for connecting them to a Wheatstone bridge. I'm going to take you a little bit ahead, and then we return to this point. Let me first take you ahead and just show you a few cases here. Now, this is what we are talking about. This is one strip. I think here they just put one strip only in this case here. This is our silica tube. You can see this tube here. And then we have, now we have these two. These are leads. These are the copper leads. And then they are connecting. If you can see properly here. First erase this. You can see here that they are connecting here to this platinum wire, which is wound around the mica, wound. Then the dummy leads, for them, they're just being short circuited. They just go back, like that. So we are going to have 4 terminals. 4 terminals. They are represented here. These are just, the connections can be made from up this side. Behind. So it's that easy. And then we have another another case here. This one you open just to expose the other parts I've just talked about. And then here, this is in a simplified version, like the one you may, if you are to do this in the laboratory. This is a center zero galvanometer. So they are here. You can see the dummy leads. For them, we just connect dummy leads. Then this and that, for them, you are winding around. You wind around these mica strips, and then at the end you should also connect them like that. It's that easy. Very, very easy. Let me return to our point here. Okay. I'll go through part by part. The platinum wire is wound on strips of mica and connected to copper leads for connecting them to a Wheatstone bridge. So we already talked about that. A pair of identical, observe this, identical dummy leads are short-circuited, enclosed in the same silica tube, and these actually, they compensate for changes in resistance. These compensate for changes in resistance of the leads to the platinum wire. As the temperature changes, that's the use of the dummy leads. This point is very important for you to pay close attention to, and I want you not to take it for granted. Don't take it for granted. Here we are. We know very well that when temperature increases, even electrical resistance increases. Now, what happens if we had not included? What would happen if we had not included the dummy leads? If you don't include the dummy leads, this is what happens. The electrical resistance of the platinum wire definitely will increase with the temperature. But remember, there is this long part of this copper wire, this one here where I'm putting that enclosure around that loop. So this other part here, which we have enclosed, for it, when the temperature increases, because it's because for it is also in the silica tube, that means its electrical resistance will also increase. Yet we are only interested in the electrical resistance of the platinum wire. So you see, we end up having errors. So what we do, the electrical resistance, remember we have two sides. We have electrical resistance we are looking at electrical resistance on our left-hand side, and then the electrical resistance on our right-hand side. We want them to balance. Now, if we don't have the dummy leads, it means that the electrical resistance shall not be entirely because of the platinum wire. You see? There is also this part here of the copper, this one here, which has connected to the platinum wire. So it means that we must also look for identical leads. We have to look for identical leads, which we have to place on the other side, so that the two, look at the position. Actually, I like Nelcon and Parker. For them, they make them, the leads actually are supposed to come up to this point here. They're supposed to come up to around this point here, so that the electrical resistance that has increased because of the increase in the temperature of the leads, these leads which are on the side of the arrow, that resistance will also be compensated by increment in the resistance of the dummy leads, so the two will cancel out. It's that easy. Please, where you don't understand, you ask. You can always reach me. My number was provided in the introduction. Okay, so we are saying that the pair of identical dummy leads are short-circuited, enclosed in the same silica tube, and these compensate. You can say, instead of saying and, you can say to compensate for changes in resistance of the leads to platinum wire as the temperature increases. Okay, next. The thermometer is connected to a Wheatstone bridge. Now, this part here is what we are calling, whenever they say the thermometer, they refer to this portion here, which has the silica tube, and then with these four leads coming out, like I already showed you that a platinum resistance thermometer, you only just see some kind of tube. There are those that are quite long. Let me show you again. There are those that are quite long, like this one here, very, very long. Very long. So it means that this is the portion for the silica tube, this one here, silica tube, and then now the other ones are just having the two leads. But you realize that here, if you open in this part here, you're going to find the four terminals. You find the four terminals for the four leads. Two are to the dummy leads, and two go to the platinum wire, just like that. Okay, now the thermometer is connected to a Wheatstone bridge as shown in the diagram, and if the resistance P equals to Q, So our point here, we say that P, the resistance of P has to be equal to the resistance of Q. Resistance P equals to Q. Then the resistance of the rheostat, here I will emphasize we use resistance box. The resistance of the variable resistor, which is the resistance box, will be equal to that of the platinum wire when the center zero galvanometer shows zero deflection. For as long as the center zero galvanometer shows zero deflection, then it means that here we are okay. Now look at this. Look at this. We are going to talk about the working. For as long as you've placed this silica tube in contact, in thermal contact with a liquid or with a solid or with, but preferably liquids and gases work better for this kind of thermometer, because for it requires being immersed into the substance. If it is a solid, you have to dig a hole in it and then you insert it inside in there. Yeah, so what I was saying is, when you connect, when you put this into the substance whose temperature is required, this silica tube here, put it in thermal contact with that body, you realize that there will be a change here. Now this one will stop deflecting. Sorry, will not show at the center. So the center zero galvanometer, instead of its pointer being pointing at the zero mark, there will be a change in the deflection. So it will go to one side, either this side or that side. So your role will be to adjust here the variable resistor. You adjust its value until this one shows no deflection. For some time, if it continues showing, it means that you have not yet reached thermal equilibrium. So you continue adjusting it. You adjust it until it shows no deflection. And when that happens, it means that the resistance of the platinum wire, which is on our left hand side, the resistance of the platinum wire actually is this side, will be equal to the resistance of the rheostat, or the resistance box, but I said you emphasize the resistance box. So the mode of operation, in other words, measurement of an unknown temperature using a platinum resistance thermometer. How do you measure an unknown temperature using a platinum resistance thermometer? So the resistance thermometer, in some books they call it, some books even on internet you find RTD, resistance temperature detector, RTD. Yeah, it's a platinum resistance thermometer, or just resistance thermometer. Is placed in a funnel containing crushed pure ice and is left for some time until the ice starts to melt. So in simple terms, we need to place it in pure melting ice. The switch is closed and the resistance box is adjusted until the center zero galvanometer shows no deflection. So the resistance R0 at 0 degrees Celsius is noted and recorded from the resistance box. Okay, and next, the resistance thermometer is then transferred to a steam bath containing steam at standard atmospheric pressure, and the resistance box adjusted again until the center zero galvanometer shows no deflection. The value of the resistance of the platinum wire, that is R100, at the steam point is noted and recorded from the resistance box. Remember, I said that here our interest is to get basically, we need to get basically, to get theta, we say the theta equals to, we need R theta, we have not yet reached here, minus R0 over R100, just reminding you, minus R0. up here was a theta, it has to cross through. Yes, something like that. Then whatever you get here, you multiply by 100. By 100. And whatever you'll get will be in degrees Celsius. So what we are saying is, get R naught. How do you get R naught? It was already here behind. You place the resistance thermometer in pure melting ice, and then you switch on. Close the switch, and then adjust the center zero galvanometer until it shows no deflection. Then get that R naught. Next, get R 100 by placing the resistance thermometer in a steam bath or steam coming from pure boiling water or boiling water at standard atmospheric pressure. It all works in the same way. And then you adjust the resistance box again until the center zero galvanometer shows no deflection. The value of the resistance of the platinum wire R100 at the steam point is noted and recorded from the resistance box. Then lastly, the resistance. Now we need the R theta, the resistance thermometer, which actually we are just interested in transferring the silica tube, is then placed in contact with a body whose temperature theta is required, and then the resistance box adjusted again until the center zero galvanometer shows no deflection. Now at that point, the resistance of the platinum wire R theta at the unknown temperature is noted and recorded from the resistance box. It will be noted and recorded from the resistance box, because we know as long as the center zero galvanometer shows no deflection, it means that the resistance of the platinum wire is equal to the resistance of the resistance box. Okay, and then we are saying that the value of theta is then calculated from that formula, which we have already talked about over and over again. Okay, now let's now focus on this. This formula is very easy to use. I've already talked about these illustrations. This is just the silica tube and that other part, but we didn't show here the for example, here this is a simple bridge in a laboratory. You look at this in paper 2. Yes, and then even this one we have already talked about these ones. Now, what are the advantages? Just hold on. By the way, supposing someone asked you to use not really using, but they may ask you to explain how you, or describe how you can measure the temperature of a substance of a body on the thermodynamic scale using a platinum resistance thermometer. In other words, how can you establish a thermodynamic scale on a platinum resistance thermometer? Thermodynamic scale. Remember, for the thermodynamic scale, we are interested in the triple point of water, and the triple point of water and the resistance at the, no, it's not the triple point of water, sorry, it is the resistance at the triple point of water and the resistance at the unknown temperature. I beg your pardon. If they ask you to determine the temperature at the on the thermodynamic scale using a platinum resistance thermometer, you will need the two values. You will need the resistance at the triple point of water, and you need the resistance at the unknown temperature. Okay. The advantages of a platinum resistance thermometer are not quite many, but here they are. It is quite accurate, very accurate actually. It is accurate as compared to, for example, liquid in glass thermometers, and it measures a wide range of temperatures, you know, for it using platinum, so you'll measure quite a wide range of temperatures. The disadvantages are that it has no direct readings, so for it you will never get direct readings. You have to keep calculating. and it is slow to respond to temperature changes. If you are using it to measure rapidly changing temperatures, then it won't work for you quite well. Now, we want now to go to the thermoelectric effect as a foundation for the operation of a thermocouple. So if two different metals such as copper and iron are joined in a circuit and their junctions are kept at different temperatures, a small EMF is produced and current flows. I will illustrate this better, but I need you to know a few points here. Let me actually include this part here. If you have two metals, so we have a piece of copper. This is copper. This is copper, Cu. And then you have a piece of iron. This is iron, Fe, ferrium. Now, if you keep them at the two junctions, so there is junction A and junction B. Now remember that these have different thermoconductivities. Copper is a better conductor of heat than iron. So what will happen is that when you hit junction A, so here we are, this is the hot junction. A is the hot junction, and then you keep junction B cold. So this is the cold junction. What will happen is that when electrons gain energy, when they are heated, they gain energy. So the electrons are going to they will gain energy, but because copper is a better conductor, so we find that electrons are going to flow through the copper faster. They're going to flow through here as compared to the way they flow through the iron wire. So at the end of the day, we realize that electrons will be flowing through in that kind of way. So they will flow through the copper wire, making this side they called to accumulate electrons. The cold junction will accumulate electrons and it becomes negatively charged. So it will be at a lower potential, to be at a negative potential. And where the electrons have come from, this will gain a positive potential because it will have lost. Yeah, these charges are just representing, please, I don't mean that they will be out there that way. No, just representing that here electrons have accumulated, then the other side they have left. Now, do you realize that now we have a potential difference? That means that there will be a potential difference that is developed here. So because of that potential difference developed, we know that now this side is negatively charged, this junction positively charged. Junction A is positively charged, junction B is negatively charged. And because of that potential difference, the electrons are going to be attracted through now this wire here, which has lower conductivity here, thermoconductivity, and even electrical conductivity. So it simply means that the electrons now are going to flow. They are going to flow through. They are going to be attracted by the positive. This one became positive, so it will attract the positive. Now you realize they will attract the negative. That was a funny statement. Sorry, didn't think about it before saying. Saying that because junction A is now positively charged and junction B is negatively charged, there is a potential difference, and because of that, the electrons are going to flow towards A. They're going to flow towards A. So you see, now we have a complete circuit. They came this way, now they are flowing. So in case you connect a galvanometer, if you connect a galvanometer, it will deflect, showing that current is flowing. That kind of effect is what we call the thermoelectric effect, or call it the Seebeck effect. Seebeck, by that man called Seebeck. So to summarize what I've been saying here, we say if two different metals such as copper and iron are joined in a circuit and their junctions are kept at different temperatures, a small EMF is produced and current flows. This is because electrons at the hot junction gain kinetic energy and move to the cold junction through the copper wire, making the cold junction to accumulate electrons and the hot junctions to be electron deficient. So as a result, the hot junction becomes positively charged and the cold junction becomes negatively charged. And the potential difference across the wire thus makes the electrons at the cold junction to move to the hot junction through the iron wire, hence completing the circuit. I've already illustrated that. And conventionally, the current flows in the direction opposite to that of the electrons. And this effect is known as the thermoelectric effect or the Seebeck effect. The pair of the junctions is called a thermocouple. It's a thermocouple. Now, the structure and mode of operation of a thermocouple thermometer. Now we want to use that effect to build up a thermometer. This is what happens. We are going to use basically, we have constant and the copper. These two have, this one has better conductivity than this one here and this one. So, okay, let me erase these things. Good. Cold junction, there is an ice water mixture, and then the hot junction. It is the hot junction which is put in contact with a body whose temperature is required, or put in contact with the steam at the standard atmospheric pressure. The setup is just this easy. Here we have a voltmeter. We can have a millimeter, a millivolt. We can use a multimeter. Or you can use, I don't know whether there is a millivoltmeter, but I think it must be there. Yes, as long as you're, even a galvanometer, as long as you're able to measure the smallest voltage that is available. Okay. Hot junction, cold junction. The cold junction is an ice water mixture. That means we have here 0 degrees Celsius. Then we have copper. 2 wires. But across one of the wires, we connect a galvanometer or an emitter that measures the voltage. I will make some illustrations now here. But okay, let me first handle this. A thermocouple consists of 2 wires of copper and constant iron, or you can have copper and iron, or platinum and a platinum rhodium alloy. For example, the one used in nail cone and Parker. So those 2 wires of copper and constant iron are joined in a circuit at 2 junctions, as shown above. Already showed you that they were joined at 2 junctions. There is this junction and this other junction. The cold junction, or what we call the reference junction, is put in a water-ice mixture, and the hot junction or the test junction is placed in contact with a body whose temperature theta is required. So you know that. Now the steady thermal EMF E naught is noted and recorded from a very sensitive voltmeter. That's not supposed to be E naught. The cold junction or the reference junction is put in a water-ice mixture, and the hot junction or the test junction is placed in contact with the body whose temperature theta is required. That means that here, the steady temperature, the steady thermal EMF E theta is supposed to be E theta. Think of panicking. E theta, E theta. So let me change that and write it as E theta. It is E, then this is a theta. So the steady thermal EMF, when you have that steady thermal EMF and it's E theta, is noted and recorded from a very sensitive voltmeter. The hot junction is then placed in steam at standard atmospheric pressure, and the resulting steady thermal EMF E100 is noted and recorded. So for a thermocouple, what is interesting is that we need 2 values. We just need 2 values. We need the EMF, the thermal EMF, at the required temperature, and then we need the thermal EMF at the steam point. So we need the E theta and E100 only. So the temperature theta on the Celsius scale is then calculated from the expression E theta over E100 times 100 degrees Celsius. Now someone will say, teacher, hold on. All along you told us, I remember very well you told us, let me increase this to reflect what someone would say. You told us that for us to get theta, we get the thermometric property at the required temperature. For example, here is the EMF. So minus the thermometric property at the ice point divided by thermometric property at the steam point minus thermometric property at the ice point. And then whatever we get is what we multiply by 100 degrees Celsius. Now, why have we neglected E naught? Why did we leave E naught out? I'm going to explain that and then we close it up. This part here equals to 0. E naught equals to 0. Please note that E naught is 0. Thing is disturbing. Is 0. Why is it 0? Remember, our thermocouple was like this. Here we have our very sensitive voltmeter like this. The cold junction is kept at 0 degrees Celsius because it's a melting point of ice. And then the hot junction is the one that we put in contact with any other body. Now if you want to determine the EMF at 0 degrees Celsius, 0 degrees Celsius. Now remember, the cold junction is already at 0 degrees Celsius. Then this one also, you put it at 0 degrees Celsius. There will be no current that flows. So it means that E naught becomes 0. That's why we only consider this part and that part, only because the other one is 0. Advantages: it can measure temperatures at a point. Yes, you can easily use it to measure temperatures at a point. You see, that junction can be put at a point as compared to other thermometers. It measures a wide range of temperatures. Yes, it really does. It measures a wide range of temperatures. It is fast to respond due to its low heat capacity. Yeah, it's quick, can respond. The disadvantages: it has no direct readings like you saw, and the EMF is affected by impurities in the wire. If there are impurities in the wire, if your wire you're using is not pure, so you easily affect the EMF. Now, I have some questions here for you. Question number 1 says a resistance thermometer has a resistance of 21.42 ohms at the ice point. So remember, resistance at ice point is called R naught. So we are given that R naught equals to 21. It's 21.42 ohms. 0.42 ohms. At the steam point, that is now R100. R100 is at the steam point they gave us 29.10 ohms. The ohms are funny. And at the unknown temperature theta, which we are going to call R theta, they have given it to us as this is what 28.11 ohms. Okay, calculate theta on this thermometer. Calculate theta on the scale of this thermometer. Definitely, because they gave us the lower fixed point and the upper fixed point, or the ice point and the steam point, that means that we are looking at a Celsius scale. So how do we calculate this? The expression is theta equals to R theta minus R naught over, complete this, R 100 minus R naught. Now if you like that, then you multiply by 100 degrees Celsius. So you can finish that. You can finish that. Just substitute and get an answer. Write the proper substitution. 28.11 minus 21.42 over 29.10 minus 21.42, whatever you get, times 100. Number 2, the resistance thermometer R theta of a platinum wire varies with temperature theta degrees Celsius as measured by a constant volume gas thermometer. According to the equation, there is an equation here that R theta equals to 50 plus 0.17 theta plus 3 exponent negative 4 theta squared. Calculate the temperature on the platinum scale corresponding to 60 degrees Celsius on the gas scale, and account for the difference between the values and state the temperatures at which they agree. State the temperatures at which they agree. I almost gave you the solution. No way. This is your question. Please do it. And the next time we meet in lesson 4, I will be able maybe to throw some highlights, but definitely not the whole solution. I want the solution. Feel free to send it to me so that I can mark your work. My number, still to remind you, on WhatsApp is 0775 374719. It's also registered on mobile money for those of you that like supporting me, because I try to give you resources freely. Thank you. Monday Dennis is my name. I wish you the best of the rest of the day. Bye bye.